Now we'll discuss about continuous probability distribution. In the previous session, we discussed discrete probability distribution function, especially binomial distribution and Poisson distribution. Those two are discrete probability distributions, where we applied combinations, factorial and combination. Here, for normal distribution, right, continuous probability, we apply for normal distribution. To understand the normal distribution, normal probability distribution function, probability, we should know some of the basics. Like before we study binomial distribution and Poisson distribution, we studied factorial and permutation combinations. Likewise, before we move to normal distribution, we studied some of the foundations like integrations, area and the curve. Right. From calculus, in calculus, where you studied limit, derivation, sometimes differentiation, and integration. From calculus to business insights, demystifying continuous probability. And also, you should know the differences between continuous probability distribution and discrete probability distribution. A discrete probability distribution, where the outcomes get a certain specific values. For example, when we toss a coin, head or tail, or predefined, right? And when we throw a 6-face die, we can get some scores. So those are 1, 2, right? 1, 2, 3 to 1, 2, 3 to 6, right? Not 0. Already defined values. And so 5, 6. When we throw the dice, the score 1, 5, 6, for example, 5 score 5 or 6. We can't get any value between this 5.1, 5.6, 5.9. We can't get it, right? When we toss the coin, we get only 2 outcomes already specified, but we can't take any value between this. This is what probability discrete distribution, discrete probability distribution. And in the Poisson distribution, we get some of the outcomes within a time or space. All of them are in discrete values. Say number of customers, we count 1, 2, 3, 5, 6, 7, like that. And number of errors, all of them are integers, not in decimal form. We can't say number of calls we receive within 1 minute, 2.6, 3.5. We can't say the number of calls 1, 2, 3, 5, 10, 20, 100, like that. Customers 20, 50, 100, like that. We can't say 2.6 customers comes to the shop. We can't say. So those binomial distribution and Poisson distributions, those are coming under discrete probability distribution. Now we are move towards normal distribution. So that's coming under continuous probability distribution. For example, average height of the students, or the height of the student. Height of the students may be 5 feet, 5.2 feet, 5.22 to 5 feet, or 180 centimeters, 175.223 centimeters. It takes any value within a range. Say, student height may range from 3 feet to 7 feet. Yeah, within this range, it gets any value. Say 3.7, 3.8, 5.10, 5.9, 5.9992, right? It's take any value. It takes infinite number of values. And student marks. student mathematical, the student marks in mathematics subject, they may get 70, 7.5, 70.5, 70.65, 90, 90.25. So they can take any values. The weight of a particular item. It may be 2 kilograms, 3 kilograms, 2.6 kilograms, 2.65 kilograms. It take any value. So therefore, it's coming under continuous probability. And let's see some of the main foundations of some foundation to prepare in-depth analysis of normal distribution. So we need to study some of the foundation. Here in business, we often need to predict outcomes over continuous range, like time, money, yeah, the sales, how much sales we are going to make in next month. So it may be 2 million, 2.5 million, 2.3 million, right? It takes any value. We represent these possibilities as a physical shape, right, or the function, right? We predict the sales, for example, the next month sales forecast. We do some prediction, for example, y equal or sales equal, next month sales equal 2000 or 200 plus 0.5x. This is a function, right? This is a sales function or demand function, like quantity of demand equal 20 minus 5p x, right? So this is what? This is a function. Continuous probability distribution, most of the time it's represented in the form of functions. So this function create a shape, for example, demand function, demand. So this is a function, demand function. This function, right, has been depicted in the form of a graph, supply function. So that's the point. This is market equilibrium. The point where a demand function and supply functions are intersected. It's a function. The rule, the total space, the area inside the shape equals the probability. Right? Here, in the normal distribution, we find probability based on the area under the curve. So this is the curve. For example, here we take a demand function like this, demand function, demand curve, and how many sales, how many demands between say a price between 2 rupees and 5 rupees. What's the demand? So this is the area. No, this is area under the curve. Likewise, in probability distribution, we will find the probability. The probability equal area under the curve. Area under the curve is very important. We apply integration function, integration, to find out the area under the curve. Look at this graph. The red line is a function, a curve, and the value of x range from a to b. The area under the curve between x value a and b, here is the area. These two are the walls. This is lower wall, this is upper wall, the bracket, right? This is a bracket. Within this range, what is the area under this curve? Understanding this foundation is very important. Here, this graph is a roof. The roof, y equal fx, function of x, right? Then that our objective of this session is the find out the shaded area. Find out the area of the area any curve, the given curve. To find the probability of any event between A and B, we simply measure the blue area. We can understand in forthcoming sessions about why do we need to use this area under the curve. This is standard integration function. This is called here integration function. Here you can see upper limit and lower limit. Always at the bottom you can find a lower limit, that is the starting wall of our shape, and the B is the upper limit, the ending wall of the shape area. Here you can see this is A, this is lower limit, the B is upper limit of the curve, the bracket. Normally this function is integration function. The area find. This simply means calculated space. And you see X is the roof, the mathematical curve that defines the top of our shape. And here the flow, the horizontal baseline we measure against. You see, this is the integration function. This is integration function, and this is the floor area, dx. We call dx. And this is A, lower limit, this is B, upper limit, this is top. So we have defined area. Mathematical definition translated here, integration AB fx dx represent the physical area under the curve fx between the boundaries x equal A and x equal B. The method, 3-step fundamental rule. First, find the primitive. Find the primitive. So we are dealing with integration, and there is an primitive mean sometimes called anti-derivative form. Anti-derivative. You might study the derivation. So you need to find the primitive. Find the primitive. Step number 1. We have to find the primitive action. Translate fx, function of x, into its primitive form. Primitive form means anti-derivative form. fx. Here, the power rule, you might study the integration. There are rules. Here, how we find the primitive form of this integration function. Here, fx. Here, this is integration x n dx. So primitive form, you can remember, right? We can write it. You can write here x. Here x, no x. We have to increase by 1, n plus 1, and this value will be come here, n plus 1, right? So this is plus c. This is the rule number 1. So it's called power rule. This is called power rule. And second, substitute the limit action, plug the ending boundary B into primitive, you see FB. Step 3, subtract the lower limit. First we have to substitute upper limit, the B, and then substitute the lower limit, that is B. Plug the starting boundary A into primitive B, and then here the final equation, here A, B. So A is the lower limit, B is the upper limit, function of x dx. So this is the form fx, function of x. If you remove the integration, here the upper limit, lower limit, then here function b minus function a. The calculation example here, lower limit is 1, upper limit is 3 x dx. So the primitive here, this is x now, here x dx. It's mean here is hidden 1. So primitive function, so x n, this is 1 no, 1 plus 1 2. So we take this 2 here, then it's 1. This is a primitive form. Limit substitute. Here first we have to substitute the upper limit and then we substitute the lower limit. Here upper limit is 3 no, 3. Here this is the primitive form, and here this is upper limit, this is lower limit. First we substitute this upper limit. Here upper limit x equal 3. Here we substitute this one upper limit, that is 3, then x equal 3. So therefore here 3 square divided by 2. So this is for upper limit, this is upper limit, and then we substitute x equal 1, the lower limit, then x equal 1 here minus, so x here 1 square divided by 2. So if we solve this, we can have 9 divided by 2 minus 1 over 2. So therefore the area under the curve is equal to 4. Area under the curve is 4. So this is the example of calculating the area under the curve. Let's see some of the properties of integration function. Visual proof you might study. Here the concept number 1. So this is the function of x. This function x is a graph function. And here concept, a line has no area. Why here upper limit a, lower limit a. Here in one point, this instance in a line, the area equals 0. Area equals 0. Because upper limit and lower limit both are same. This means there is no space. Without space we can't find area. It's logic. And constant multiples. Constant. Here multiplying the function by k scales the area by k. Here this function, right, the k, constant, and function of x. In this instance, we can bring this k from outside here, and then we can do the normal calculation. So now this form has become into this form. Earlier, right, so without constant, the area is like this, area A to B. If we introduce k scale, it's go up by k. The multiplying the function by k scales. K is a constant. And rule number 3, reversal of the limit. Normally we find the area from lower limit to upper limit. Lower limit to upper limit. So A is a lower limit, B is an upper limit. So this is the standard form. This is standard form. Here, for example, say this is AB, no, AB area under curve is this. If we reverse it, if you reverse it, it's get the negative value. If you want to reverse here, earlier this form is here in this form. Upper limit is A, lower limit B. Actually, it should be another way, right? When we reverse it, here, instead of B, we put, so instead of A, we put B here, and for B, we put A. Earlier, upper limit become lower limit, and earlier lower limit become upper limit. Upper limit become lower limit. And that in scenario, here we have to put negative function. That's one. And splitting. Initially, the lower limit is A, and lower limit A, upper limit B. Now we divide into two parts, A to C and C to B. So how we can represent it? Here, this is original form, A to B, the area under the curve A to B. Now we can divide this A to C plus C to B. The concept is two sliced areas sum to the whole. These are the basics rules. Now we bridge how this integration function can be used in the probability function. The bridge, when area becomes probability. Look at here. This is the curve. This is curve, function of x. The total area under a curve, right? The total area under a curve is 100% or 1. Total area always of any curve equal 1 or 100%. So that value, the x upper limit and lower limit, it takes any value, infinitive minus to positive, infinitive. Anyhow, the total area that the curve is 1. This is a rule in the probability. It may not true in other context, but when we study the probability, we know that probability lower limit is 0 to 1. We use the area under the curve to find out the probability, and we restrict the maximum value of the probability is 1. So therefore, we apply the area under the curve, no? So therefore, we limit the area under the curve maximum 1. And it never goes to below 0. It means no negative value. Probability has no negative value. The magic condition, if the total area under a function fx, this is function of x. Fx means, for example, here 2x plus 3. For example, this is what? This is a function. This is function. Normally we call them function of x. We write this function of x. If the total area under the curve of function fx from negative infinity to positive infinity equals exactly 1, then that function describes a continuous probability distribution function. As I told you earlier, the probability limits between 0 to 1. Why we limit to 1? Because 1 represents 100% certainty. Every possible outcome exists somewhere within that boundary space. Every possible outcome exists somewhere within the boundary space. So total, if it is 100% sure, then 100% no, it means equal 1. No chance, impossible, probability equals 0. And the probability may lie between 0 to 1. any space. The implication, by forcing the total area to equal to 1, measuring any subsection of that area give us the exact percentage chance or probability that a specific event are occurring. For example, here the maximum value of x, here 2, for example, 2 to 6. Assume that the maximum value, the two extreme values of x, 2 and 6. Between these 2 and 6, the total area equal to 1 or 100%. Now we can find the area. For example, the area, here 3 and 4. 3, 4. So we want to find the area between these two, 3 and 4. In that instance, we just find the area under this lower limit and this upper limit. This area is what? Represent probability. It is definitely less than 1. The total area from 2 to 6 equal 1 or 100, and any sub area between a value here 3 to 4, it's definitely below 1. Two different world. We are handling two different world, discrete and continuous variable. Discrete variable, as I already explained you, it takes a specific values. Continuous variable in any range, right? And in a certain range, it takes any infinite number of values. Discrete, we can count numbers. Nature is what? Variable that take exact distinct value. For example, inventory item. How many inventory items? How many bags? How many coconut? How many apples? How many bricks? How many tables? Number of employees? How many staff? How many minor employee? How many executive staff? How many board of directors? Core rules, the probability for a single exact value exists. For example, when we throw a 6-face die, its outcomes are 1, 2, 3, 4, 5, 6. Each value, say for example 1, getting score 1, it has its own probability, 1 over 6. Value 3, score 3, it has its own probability, 1 over 6. When we toss a coin, probability of head, the head has its own probability, 1 over 6. The formula is probability of x in discrete variable is more than 0. Continuous probability distribution, nature, variables that can take any real values within an interval, time. So between 9 to 9:30, 9 p.m. to 9:30 p.m., how many times we can take? 9, 5, 9, 10, 9, 25, like that. Even 1, 9, 10, 2, 3 milliseconds, microseconds, nanoseconds, right? So it has infinite numbers. Distance, kilometer, from A to B, the distance, right? Say some could say 2 kilometers to the A to B is 5 kilometers. In that range, it takes any value, 5 kilometers, 2.2225 kilometers, 2.333369999 kilometers. So it takes any value. The weight, like kilograms, grams, milligram, nanogram. And the core rules is probability for a single context point is 0. Right? You should remember in discrete probability distribution, the individual value has a probability, certain probability, but in continuous probability distribution, one point has probability equal to 0. The probability for the single exact point is 0. Probability is calculated only over an interval, right? That's why here the rule here, you see at this point probability area equals 0, no? Area equals 0. So probability equals 0. Here upper limit A, lower limit A. For example, upper limit 3, lower limit 3. Between there's no space. No space means no area. Area equal to 0. Then when we apply this with the probability also 0. So that's what it explained here. Probability is exact. Probability is calculated only for an interval. Probability is 0 for an exact point. The formula here probability of x here, some right for a certain point equals 0. Certain point. We find probability for an interval. The rule book, precondition of probability density function. There are 3 rules. Condition number 1, non-negativity. As I told you earlier, the probability should range between 0 to 1. It never goes below 0. It means no negative. When we translate this, the curve, right, the red curve must never dip below the floor. So it can't go like this. Or it can't go like this. No. Maximum, right? Here, this is the limit. So it never crosses the floor, x-axis. The red curve must never dip below the floor, the x-axis. You cannot have negative probability. That is rule number 1. Rule number 2, the condition number 2, total probability condition is 1. Right? It takes any value, infinitive, any large number, any lower number, right? The maximum area under the curve is 1. The total space under the entire curve must equal exactly 100%. The total area is 100%. Condition number 3, interval probability. Here, so this is total area, no? 100. Any area between 2 walls, 2 range, any, right, has some probability. Here, probability of x that between A and B. So we can find the probability like this. The area, the probability, right? Probability equals the area, or area equal probability. This is lower limit. This one, this is upper limit, and the function of x, the dx. The probability of an event falling between bounds A and B is calculated by finding the area between these 2 walls. But here the area between 2 walls, here the area between 2 walls is the probability between A and B. Let's see some of the applications. First, we will discuss the uniform distribution, the simplest probability distribution function. Uniform distribution, right? the straight line. What does uniform mean? Equal density for all values. The roof fx is perfectly flat, a constant. For example, here, what's the function of this curve? What is the function of this curve? Y equal 0.5. So normally a curve like this, no, y equal a plus bx. But here, right here, the uniform distribution here means it has only this value, and here we can't see this absence of this, right? So uniform distribution has only this one. For example, y equal 2 means in the graph we can draw like this. So this is the graph. So this, we couldn't find this area, means it has no slope. No slope. No slope. Slope equals 0. So that's why we have only the constant. So this kind of probability, this kind of graph is called what? A uniform distribution. This kind of, to represent a uniform distribution, probability distribution, this called what? Uniform distribution. So what does uniform means? Equal density for all values. The roof fx is perfectly flat. It's a constant. The setup, suppose a variable is distributed uniformly between 0 and 2. So lower limit is 0, upper limit is 2. So the fx, c means we have only the constant like this or like this. Finding the roof, the height. So sometimes they may not give us the roof, the constant. Here, this is a function, right? The function fx equals z, fx equals c, but the x, value x, range from 0 to 2. X range from 0 to 2. We know that, so where c is an unknown constant. Otherwise, it's 0. Otherwise, equals 0. If the x takes any value above this range, for example, 2.1 or 3 or 5 or minus 0.1 or minus 2, then it becomes 0. The area becomes 0. Here, it's written like this. Here, now how do we find the height? Here, how do we find the value here? The only given information is this, fx equals c. So what's the value of c? And also it's given the x value range from 0 to 2. So finding the roof, the height, that's mean the constant c, this is c. By the total probability rule, area equal 1. We know that the total area equal 1. That area range from where? 0 to 2. So the area, normally the area equal what? The base to height. This is the base. This is the base and this is the height. We don't know what the height is. So so this is base, this height c, and this floor, this base is 2. 2 means what? 0 to 2. So area equal base into height. So base, we know that base is 2. This means from 0 to 2. So height is c. So must be what? C must be half. Why half? We know that area equal 1. area always equal to 1. We know the base 2, right? Like this, 1 equal 2 into C. So C equal what? C equal 1 over 2. So easily found the value of C, the height. Resulting, so if the area is equal to 1, then we can say that that function is what? Probability, then a distribution function. Probability distribution function. Here fx, now we found what is the value of C. C is 0.5. Now we found fx 1 over 2 for x 0 to 2, otherwise 0. So it can be written in statistics like this. It is written in this form. Right? You can see when you take the past papers of statistic, you can find this kind of notations, statistical notation. So how we can read this? Here, this is function. This is fx. Here fx here is given only constant. It's given only constant and it has no slope. So therefore it is what? It is uniform distribution. It's a uniform distribution since we have no slope. But the range, right? The minimum value is 0, maximum value is 2. If x take any values beyond this, the probability is 0, right? The area could be 0. Otherwise 0 means if anything violate this rule, then it becomes 0. X become 0. Area becomes 0. Yeah. So this is the normal function. Here fx equals C. Right now, if we integrate this C dx, no, C dx. Now, according to the rule, we can bring this C out. So therefore, C integration, we know that x equals 0, no? Already x equals 0 dx. So the hidden x equals 0. X equal x 0, right? X power 0. Then C, right? X power 0 always equal to what? Equal to 1. Equal to 1, right? Equal to 1. 1 over 5. So this is one thing. Right here, we have upper limit 2, lower limit 0. So if we substitute x, and here it has two forms now, x0, now it's become x1 over 1. Now we can substitute upper limit and lower limit. Upper limit 2, lower limit 0. Then here first we substitute this upper limit. Here x equal 2. So in this instance 2 power 1, and we substitute the 0, x equals 0, and in this instance 0 power 1 and 1. So this is 0, this is 2. So 2 minus 0 equal 2. Right? Therefore, what? So we can take 2 into 2. So 2c equal. So here 2c equal. Here when we substitute this, we can take this. So 2c equal 1, then C equal half. Now, let's see the case scenario. The waiting time at a customer service center has a uniform distribution from 0 to 2 hours. It means if you take as a shop or any service customer service counter, normally the customer wait 0 to 2 hours, maximum 0 hours, 0 waiting, and maximum 2 hours waiting. This is a scenario. The question, what is the probability a customer wait between 30 minutes and 90 minutes, or for half an hour, or 1.5 hours? So normally the range is 0 to maximum they wait 2 or they are not waiting. We want to find out the probability that what's the probability? What is the probability of any customer that wait half an hour or to 1.5 hour in that range? So that instant here we know that the lower limit is 0.5, upper limit 1.5. So hours, so 30 minutes, 90 minutes. Here we substitute in the integration function. Lower limit 0.5, upper limit 1.5. For integration function means area. We know the C. C is 1 over 2 or 0.5 dx. Now we bring out this 2 here and we substitute 1.5 and 0.5. So how we can do this? Let's see. This is a function of 0.5 dx. 0.5 dx. Now we bring this out. So 0.5 and x0 dx. If we get primitive 0.5 here, x1 over 1. Now we have upper limit 1.5, lower limit 0.5. Now we substitute x equal 1.5. Then, so x 1.5 power 1 and this is 1. And we substitute 0.5 second lower limit x 0.5 over 1. So 1 minus 1.5 minus 0.5 equal 1. 0.1. Then, and so this area, now we can say 0.5 here. Now we found 0.1. Yes. Yeah. So 1, right? So we found 0.1, 1.5 minus 0.1. So 1. Already we have here 0.5. 0.5 into 1 equal 0.5. So area is what? 0.5. This means area equal to the probability. Then probability equal 0.5. Yeah. This means the area between 0.5 to 1.5 is 0.5. We already know the area between 0 to 2 is 1. This means a customer wait 0 hours, 0 minutes or 0 hours maximum 2 hours. That is a uniform distribution function. Total area 1. Now the question is, what is the probability of a customer who is wait half an hour to 1.5 an hour? So the probability equal 5. There are 50% chance a customer may wait 0.5 to 1.5 hours. 50% chance. Here, the target area is this 30 to 90 minutes. 30 to 90 minutes. The calculation, the probability 0.5, 1.5. So we use this one, this formula. The interval, the length is 1. The probability, the length into density, the length here 1, density 0.5. So there are 0.5. The manager insight, exactly 50% of all customers will receive service within 1 hour. So this 1 hour. It's mean waiting half an hour to 1.5 an hour. So it's 1 hour. Normally 50% of the customer should wait half an hour. So 1 hour. Half 1 hour, right? Any doubt here? Any questions? Any questions? Right. Now we move the second example. The example is this. The probability density function for a random variable x is given here. Look at here. Earlier, in earlier previous example, this part is not given. They give us only this constant k. Has no slope. That's why it's called uniform distribution function, like this earlier. Now it has some slope. So since it's a square, and also it has constant, so it start from here and somewhere like this, or like this area. So if you want to find the probability, we have to find area under the curve. But here the range is given. What's the range? It goes up to -1 to +1. If x takes any value beyond this, beyond -1 or above 1, it becomes 0. The area becomes 0. This is the meaning of this. Now you can read this. The probability density function fx 3/4, that's constant, 1 minus x square, x range -1 to 1, otherwise 0. Probability density function. Here, probability under the curve. So when we draw this, here it's look like this, the curve. When we draw this, it's like this. The curve, in reality, probabilities are not flat. It is not uniform distribution function, right? We have completed uniform distribution function. In reality is what? Probability is not always flat. In reality, probabilities are not flat. They peak and taper. Here, the probability density function is a smooth dome. This function here 3/4, 1 minus square. We can see this. You can see here the function is given here. Fx is this, and its range -1 to +1. Here -1, you can see -1 and +1. So beyond that, 0. Otherwise 0. That's called otherwise 0. So probability density function here, the top 3 over 4. This is what? 3 over 4. And 1 minus x square. Now we verify. We need to verify area under this curve that range from -1 to +1. Area should be equal to 1. Here we need to verify. How do we verify? Here the minimum point is -1, maximum point is 1. And the k 3 over 4, 1 minus x square, so dx. So if we find the primitive, we can bring this 2 over 4 outside. This is k, no? K. So we can take this outside and only this part remains here, x. So here we can write this here, x0, no, x0 mean 1. So that's why this x disappear. Now we already take this outside, and x0, no, x0 mean when we make it primitive form, 0 plus 1 has become x1 over 1, and x square become cube, and this 3 become here. And upper boundary is 1 and lower boundary -1. So first we substitute x equal 1, then this is 1 minus 1 cube 1, this is 3. This is lower boundary, and minus upper boundary, we substitute -1 for this x. So we take this value. Finally, we take this and we multiply with this. We can get 1. Total area is 1. The rule hold. So this is what? It's a probability density function. We can use the calculator as well to solve this one. Right? You can prove this here. Here, yeah, 3 over 4, right? 3 over 4. And we should use this integration function, and that is 1 minus x square. And the lower boundary is -1, and the upper boundary is 1. You see, when we solve this, exactly 1. Right? The area under this function, under this curve, is 1. So this rule satisfies the probability requirement. Now the question is finding the specific probability. Now here we know we proved that the area between -1 to +1 is 1. Area is 1. Now the question, what is the probability range from 0 to 1? So this area, we need to find out this area 0 to 1. So here, find the area. This is the function of x, and the upper limit is 1, lower limit is 0, as here. Upper limit 1, lower limit 0. So if we substitute, first we need to find the primitive form, antiderivative form. So we bring this outside. It's a k. So x power 0. So if we substitute this, and we get 1 over 2. So area under this curve right? Area and in this range 0 to 1 is 1/2. So exactly 50% probability lies on the right half of the dome. Right, now we use the calculator to prove it. To prove here, now we change this value. Yeah, it is 0, no? It is 0. It is 0. You see, 1/2. We get exactly same. In examination, you have to write the steps. You can use a calculator to verify your answer, but you have to write each steps. And now let's see this one. The K puzzles ensuring valid probabilities. Now, so look at here. Question is given to you. Example. X is a continuous random variable. X is a continuous random variable. Its probability, a density function, PDF, is given in this form, fx, right? Function of x. Here, the k, the constant value is given. Constant is given, but the value is not given. The function is what? K constant 2x plus 1. But the x will range only from 0 to plus 2. If the x value takes any value other than this range, the probability will become 0. Right. Now, we have to find the k constant. How do we find the constant? We know the rule. What is the rule? Probability, right? Area between 0 to 2, k 2x plus 1 dx equal 1. So this is the rule, probability rule, total area. No? The maximum, the x, where x range from 0 to 2. 0 to 2. The area under this 2 range, the interval equal 1. In that rule, we can find the value of k, value of this k. Here, so this is the thing. Upper limit is 2, lower limit is 0. The k is a function, k is a constant, and this is the x value. And we know that it's equal to 1. Now we bring this k out. So it's here. Now it's 2x plus 1 dx 1 equal 1. Now we find the primitive form, right? Primitive form. How? Here x, so 2x, then already 1 here, here x 0 here. Then when we write this, here 2x here over 2, and here plus x 1 over 1. So if we cut this 2, then x square plus x. So this is the primitive form. This is the primitive form. Now we substitute upper limit and lower limit. So k is constant. Here this is the primitive form. This is upper limit. This is lower limit. Area equal 1. Now we substitute. First we substitute 2 for x. So therefore 2 power 2 plus 2. This is, we substitute the first part. The second part, we substitute 0. Then 0 power 2 plus 0. Altogether, this area becomes 0. So therefore, 4 plus 2 equal 1. So we remember we have k. Therefore, 6k equal 1 and k equal 1 over 6. So now we found value of k. Then we can substitute this k. We can substitute this formula. We can substitute here. For this k, we can write 1 over 6. So this is the probability density function. If you draw this in a graph, it's look like this. You see the constant cut here, cut y-axis. That is 1 over 6. Now this is this function 1 over 6. 2x plus 1. It ranges from 0 to 2, otherwise 0. The problem, the continuous variable has probability density function k 2x plus 1 or 0 to 2. So we found k equal 1 over 6. The absolute law of total area equal 1 allows us to reverse engineering incomplete models. So here this incomplete is a given, initially given model. So this is what? This is incomplete model. We have to assign the value of k, because we know that probability, we know to find out the clue is what? To find the value of k, probability equal 1, area under the curve 1. Now the question is 1, 2, 3, 4. Here we have found the k, value of k equal 1 over 6. The another question, probability, what's the probability? That is x value take 0.5. So it is within the range, 0.5 is within the range. So what's the probability? So here, this is the graph, no? This is the graph. So it's at the range 0 to 2. Here it's given 0, minimum range 2, maximum 2. Now the question here, if x equal 0.5, so this, and x is larger than that. So we need to find the area. So how we can find it? Very simple. Lower limit now 0.5 and maximum limit is 2. Then the function is what? 1 over 6 2x plus 1 dx. So the value is what? The probability. We can work out here 0.5. Here is a function, and we take out this 1 over 6 from outside, and this is become right, x square over 2, and this 2 comes got here, it's plus 1, and first we substitute 0.5. Sorry, this is question is this, right? Is less than, right? X is less. I'm sorry. We have to find a probability area of this. We have to find the probability. Actually, this. I'm sorry. Already, I say like this area. This area, that's wrong. We have to find the area of this. So the lower limit is 0. Upper limit is 0.5. So for this one, this area, actually we want this. So therefore 0 to 0.5, 1 over 6, 2x plus 1 dx. So that's represent this area. Right. So here we found the probability. That is what? 0.125. I can tell you how can solve using the calculator. Here, yes, 1/6. So sorry, integration. The function is yeah 1/6. 1/6 and x bracket 2x square 2x, sorry, 2x, not square, right? 2x plus 1 plus 1 and lower limit is 0, upper limit 0.5. So 1/8. 1/8 mean what? This is 0, 1 to 5. The next question, probability x above 1.5. So very simple. We change lower limit is 1.5, upper limit 2. Upper limit 2, lower limit, sorry, lower limit 1.5, 1.5 and upper limit 2. What is this? 375. Right here 375. We got the same answer as well here. And the third question, the fourth question is probability 0.5, probability between x 0.5 to 1.8. So if you use the calculator for the time being, here upper limit 0.5, upper limit 1.8, lower limit 0.5. So that is 715. Area 715. Yeah, is here 715. Right. Some of you are messaging me classes.